We had some homework last night on page 572, but before we check that homework, I'd like to take a look at one question that relates to stuff that we've done, not yesterday, not the day before, but over the last several days. Page 569, number 12, this question right here. I'd like you to have a read and then see what you can do with that question over the next 60 or 90 seconds, and then we'll take a look at it as a class. Aaron, what's the answer to that question? Yeah, good. We've got a ring here that's charged. And of course, that ring that's charged with a bunch of extra negative charges will eventually, and that, I mean, when I say eventually, it's going to be pretty quickly, going to reach a point of static equilibrium. And when it does that, those electrons, those extra electrons, are all going to go to the outside surface. As they go to the outside surface, this electroscope, which of course just simply detects charge, not the type, not the amount, but just detects charge, it's going to detect charge on the outside of the surface. This electroscope, which is attached to the inside, is going to detect nothing because there's no charge on the inner surface. It all goes to the outer surface. If I had some kind of electric field detector, not a charge detector, but an electric field detector, and I measured it out here, okay, at this point, X right out here, would I find there's an electric field? Yes. Nick's right, there is an electric field there, right? And the electric field would point inwards toward the surface there, right? What would the electric field be right inside here if I was to measure that? James, what's the electric field right there? No. Pressure? What's the electric field inside there? Right, 0. Okay. The electric field inside the conductor will be 0 because it cancels out, right? Make sense? Good. Why doesn't it, hey, if it cancels out on the inside, why doesn't it cancel out on the outside? I mean, it's the same object, right? It cancels on the inside, shouldn't it cancel on the outside? Well, if we pretend there's 3 charges here on the inside, let's say right here, and right here. There's lots, but it's a lot simpler to draw a diagram with 3 field lines than it is with 30 field lines. First field goes this way, second field goes this way, third field goes this way. They cancel each other out, right? Ultimately, if you did a vector analysis, it would cancel each other out. On the outside, you got one that goes this way, you got one that goes this way, you got one that goes this way. Those don't cancel each other out. Okay, there's no way that those will cancel each other out. So the field will cancel out on the inside. This Faraday cage has no electric field on the inside, but on the outside, same as it's always been. There's still that same electric field that there's always been. Yesterday, we introduced that whole concept of charges accelerating in an electric field, speeding up or slowing down in an electric field. And we said that whenever we see a problem involving a charge speeding up or slowing down in the electric field, then we can treat it just like a physics 20 problem, a relatively easy physics 20 problem. When a charged particle speeds up, it's just like a car going down a hill. Because a car speeds up when it goes down a hill, right? When a charged particle slows down, it's just like the car going up the hill, because that's what the car does as it goes up the hill. In both cases, we would start off by saying EI is equal to EF, whether it's speeding up or slowing down. If it's speeding up, then we must start off with potential energy. If it's gravitational, because you've got the car going down the hill, then it's going to be mgh equals 1/2 mv squared. If it's electricity, the charge speeding up, then we'd replace mgh with qv. If it's slowing down, well, then we got to start off with kinetic, because you can't slow down if you don't start off with any kinetic energy. It's got to have a speed in order to slow down. We would say kinetic energy in this case is converted to, well, in the case of the car going up the hill, gravitational potential energy. In the case of a charge slowing down, it would be electric energy. Now, there's times when the equations look a little bit more complicated than this. Maybe you have to add in a 1/2 mv squared on the left-hand side. When would we do that? When would we add in a 1/2 mv squared on the left-hand side there, Cassidy? Good. In other words, when it starts with a potential difference, it's going to go across the potential difference like the car going down the hill, but it's already moving at the beginning of the problem. Then we tack in the 1/2 mv squared. Okay, when would we tack in a 1/2 mv squared on the right-hand side of the second problem? You're slowing down, but we're tacking on a 1/2 mv squared right there. Stephen? Sorry, I thought your hand was up. Jace? When do we tackle 1/2 mv squared on the right-hand side over here? No, not necessarily. No, not necessarily. We're slowing down here. So it is slowing down, but basically, even if it reaches the other plate, it's slowing down but still moving. So in other words, it's like, a car is going up the hill, it reaches the top of the hill, but it hasn't just barely reached the top of the hill, it's still moving when it reaches the top of the hill. What about this? What about tacking on a QV over here? When would we tack on a QV onto the right-hand side of the first equation? Remember, speeding up, car's going down a hill. When is there going to be potential energy at the end of the problem when the car is going down the hill? Okay? Right, when it hasn't gone all the way down the hill, or in a case of a charge, when it hasn't gone all the way through the potential difference. And finally, when would we have, it's not very often that in this situation we'll have a QV on the left-hand side, but it's possible. Cars going up the hill. When are we going to have potential energy at the beginning of the problem when the car is going up a hill? Lucas? Right, so it's not starting at the bottom of the hill. Good. Make sense? Okay, the homework questions that we had last night were page 572, number 1 and 2. Any issues with either of those questions? Who's got it done? Nobody had any trouble? Okay, I'd like to do one of them, even if nobody did have trouble, I'd like to do one of them just as an example here. Do you have a preference, 1 or 2, or should I just pick one? Number 2? Okay. 2 says if a charge of negative 6.0 times 10 to the negative 6, should have made that red actually, times 10 to the minus 6 coulombs gains that much kinetic energy as it accelerates, what's the potential difference between the two parallel plates? So we've got a charged particle accelerating. That's like a car doing what? When a charged particle speeds up, it's like a car, Aisha, going down the hill. So when a car is going down a hill, we start off by saying EI is equal to EF. We start off with potential energy at the top of the hill, and we end up with kinetic energy at the bottom of the hill. Well, we're going to sub in QV for MGH, right? Because we're not dealing with gravitational potential here. We're dealing with electric potential. You don't even have to write in MGH and cross it off like I did there. If you want to, you can just go straight to QV. That's fine. Honestly, if I was doing this myself as an answer key for a test or something, I wouldn't have put in MGH. But that's because I've done it a million times too. Okay, if I was in your position, I might. What are we looking for here? It gains that much kinetic energy. What's the potential difference? Oh, we don't actually need the 1/2 mv squared in there, do we? How could we simplify this a bit? Aiden, is your hand up there? All right. Sounds familiar. Aiden, how could we simplify this a little bit? What could we do instead of putting in 1/2 mv squared on the right-hand side? Stephen? Yeah. It's not wrong to put in 1/2 mv squared there, but if we already have the value of the kinetic energy that's gained on the right-hand side, then let's just put it in. QVI is equal to 1/2 mv squared, or QVI is equal to 3.2 times 10 to the minus 4. The charge is 6 times 10 to the minus 6. Oh, but it's negative, right? Times the initial potential. Is that right? Do we ever put the sign of a charge into an equation? Drop that. Drop the sign of the charge, right? 6 times 10 to the 6 times VI is equal to 3.2 times 10 to the negative 4. Let's divide 3.2 by 6. And when we do that, we should get 53.3 volts. Now, technically, I haven't found the potential difference. Technically, what have I found? Jake, what have I found there, technically? The initial potential, right? Remember, the potential difference is the difference between initial and final. I haven't found the difference. I've found the initial. But if we assume the final to be 0, then the initial is going to be the same as the change, right? It's the potential difference. And that's always going to be the case, right? If you assume the final to be 0, then the initial potential will be the same as the potential difference, always. All right? We're going to have you look at a few questions here on page 570, not this one. Yeah, that's right, page 575. The questions that I want you to take a look at are questions number 1 to 9 and 11 to 12. Those are going to be homework, but you're going to have quite a bit of time here to work on those today. Okay? I do have one more example question that I want to go through with you, just as a more of a thought question, as a bit of a challenge question. Okay, but other than that, you're going to have time to work on these questions in addition to worksheet number 9 that was assigned yesterday. Those will be homework for Monday. We'll spend some time either Monday or Tuesday reviewing for our test, and then we'll have our test, as we decided yesterday, on Wednesday of next week. So let's give these a try here right now, and then we'll answer some questions on them a little later on. If we have any questions, we'll do another example question a little bit later on, and then we'll call it a day. Here's the last question that I want you to take a peek at here. Again, this is not something that we will necessarily see. It's just something to get our minds moving a little bit more. It says an electron enters the electric field between two charged parallel plates, as shown in the diagram. We want to first take a look at A, sketch the motion of the electron between the plates. This reminds me, when I see this question, of something else that I've seen a number of times. A ball rolls off the edge of a cliff in a gravitational field that points downwards. What's the shape of that path of this ball as it goes through that gravitational field? Curves downwards. Anybody remember the mathematical term for it? It's a parabola, right? People see this one and think, wait, a negative charge will experience a force opposite to the field, right? So it'll accelerate downwards. So they have this feeling that it's going to go like this, and then when it enters the field, it's going to go straight downwards. Well, it's not going to go straight downwards any more than the ball would go straight downwards, right? It's not, what's the cartoon? Is it Wile E. Coyote that runs off the edge of the cliff? Always? Right? And he runs off the edge of the cliff, he looks down and then falls straight down. What doesn't happen in gravity, it doesn't happen with electricity either. So this electron, as it went through there, would experience a downward force, but that downward force would have the same effect as the downward gravity force on Wile E. Coyote and cause the electron to go something like this. The shape of that path would be a parabola, just the same as that shape of that path would be a parabola as well. Does that make sense? Again, another similarity between gravity and electricity, right? The shape of the path of a charged particle going perpendicular to the field will be the same. It'll be a parabola. All right, if we're solving the problem, to solve for the time taken in the Wile E. Coyote problem, and then we would do this. X and Y components, we describe the X component by V is equal to delta D over delta T, simply because horizontally, Wile E. Coyote doesn't change speed. There's no forces acting on him horizontally, just vertically. So constant velocity, V equals D over T. Wile E. Coyote's vertical motion would be described by this equation, or one of the other acceleration equations, VIT plus 1/2 AT squared. Well, if the object experiencing the gravitational field going in a parabola can be described by that equation, then the object experiencing the electric field could also be described by that equation. I talked about this with my physics 20s last year. I don't know if you remember, those of you who were in my class. And I'm not sure if Mr. Coder would have talked about this or not. It's not something that we needed to know. But if you look at the shape of this path, it's a parabola, right? James told me it was a parabola just a minute ago. Take a look at this equation. You guys have all done parabolas in math class by now, right? The equation that describes a parabola is y is equal to what? sorry, ax squared plus bx plus c. Remember that from math class? Remember that? Does that ring a bell for anybody? All right. Well, if we change this equation around a little bit, change that from delta d and make it df minus di, and take the di over to the other side, and change the order of this a little bit, it ends up being 1/2 at squared plus vit plus di. So in other words, the y position is equal to your coefficient a. Your x on your graph of your parabola would be time. Vi would be your second coefficient. X, again, would be your time on your x-axis. And di, your initial position, would be c in your parabola. So this is the equation for a parabola. D is equal to VIT plus 1/2 AT squared is the equation for a parabola. And that's why we use it to describe projectile motion, because it's a parabola equation. Anyways, that aside, we could use both of these equations to describe what's going on here. Horizontal velocity, we don't know that. Horizontal displacement, we don't know that. Time, we don't know that. So the x component doesn't seem to be very useful to me, at least right now. Let's go to the y component. dy here would be negative 0.010. Look, because we're trying to find the time that it takes for the electron to travel this far vertically, 0.010 meters toward the positive plate. Vi would be 0 because we're looking at the y component and it's moving horizontal as it enters that electric field. Acceleration would be negative 2.00 times 10 to the 17 because it's accelerating downwards. And then we solve for time. Yeah, I'm not even sure what the time works out to be there, and I don't really care, to be honest, what the number is there. It's the process that we've just gone through that's the important thing to me. Does that make sense? Again, it's just another example. I looked at your test this morning. It's been a while since I've made the test, and so I couldn't remember exactly what was on it. There's nothing like this on there. There's nothing like this on the test, and I doubt you'd see something like this on your exam either. Again, it's not why we're doing it. We're doing it just to, oh yeah, hopefully when you see it, it's like, yeah, that kind of makes sense. So then you become just the tiniest bit smarter than you were 5 minutes before that. Okay. Every time something makes sense to you, you're smarter than you were before. Okay. So what's your homework for the weekend, guys? Those check and reflect questions, right? And worksheet number 9. Okay. That's it for today.